So in this video, we're going to look at so-called anisodesmic compounds. Anisodesmic. So what does that mean? Aniso means unequal. And then desmic is Latin for band or chain. Here it refers to bonds in this context. So we are looking at compounds that have unequal bonds, where the bonds are not equal in strength. That's the way in which they are unequal. And we were going to look at carbonates as an example. Let's erase the chalkboard. So for the carbonates, they are based on the anionic complex CO3. Let's first evaluate the charge. Carbon has a 4 plus charge, oxygen is 2 minus. So the total positive charge here is 4 plus and 6 minus over here. So the anionic complex has a 2 minus charge overall. So if we have a carbonate unit with an overall 2 minus charge, how might we balance that? Well, we could balance it with a calcium 2 plus, and that would give us calcite, CaCO3. But we can balance it using other 2 plus anions. For example, iron can have a 2 plus charge, and if we balance the carbonate anion with iron 2 plus, then we would get the mineral siderite. And there are many other options for balancing this carbonate with a 2 plus cation. For the case of the carbonates, we have a carbon which by observation we know is in threefold coordination. So we'd write carbon with a Roman numeral 3 as a superscript. That means the carbon is going to be bonded to 3 anions. There's only one kind of anion in calcite, and that's oxygen. And oxygen, again, it has a 2 minus charge. So we'll draw them over here. Now let's take a look at the electrostatic valence bond strength for calcite, at least for the carbonate unit on calcite. Carbon has a 4 plus charge. It's being divided between 3 different bonds, and so each bond gets a plus 4/3 or a plus 1 1/3 charge. So that means that this carbon here, its 4 plus charge is going to be divided in this way. It'll send 1 1/3, not 1 1/2, 1 1/3 to that oxygen, another positive 1 1/3 in this direction to that oxygen here, and then finally another 1 1/3 positive charge to that oxygen. So that takes care of the total 4 plus charge on this guy here. But take a look at what that means for the oxygens. Let's take a look at this oxygen down here. Let's say this fellow is going to be bonded to calcium, and it will be. Calcium has to come into play somewhere. So if we have 1 1/3 charge being neutralized here, if of this -2 charge, if 1 1/3 of that negative charge is being neutralized by that bond, then how much negative charge is left to be donated to this calcium ion here? And the answer would be minus 2/3 charge. So there's a symmetry here. If we have, well, there's an asymmetry in the red and white direction, but there's a symmetry in this sense. So if there's a plus 1 1/3 charge being sent this way, then there is a minus 1 1/3 charge being sent from the oxygen back to the carbon. So that's where the symmetry is. That symmetry is being broken over here in terms of the magnitude of the charge. If we absorb 1 1/3 of the total charge here, we only have a minus 2/3 charge left. That's a minus 2/3. That will allow calcium of its 2 plus charge to send a positive 2/3 charge in that direction towards oxygen. But the big issue here is, remember, the electrostatic valence bond strength, EVBS, is proportional to this ratio here, the charge divided by the coordination number. And with only 2/3 here for our electrostatic valence bond strength between oxygen and calcium, then that means the calcium-oxygen bond is much weaker than the carbon-oxygen bond. So we started out by using this term anisodesmic, unequal. And this is what we mean. We mean that the calcium bond here, the calcium-oxygen bond, is much weaker than the carbon-oxygen bond. So let's erase the chalkboard again. So if we take a look at something like calcite, CaCO3, we can predict that it should dissolve into calcium ions plus carbonate units, that these will maintain their character here. These carbonate units will maintain their structural integrity. It's the calcium that will break off from the oxygen, not the carbon, because that carbon-oxygen bond is much stronger than the calcium-oxygen bond. So the study of anisotosmic compounds and the differences between relative strengths can have some very powerful implications for trying to predict how things will dissolve or react, what kind of ionic units will be developed when we have different kinds of chemical reactions.